Hi, welcome. My name is Johan Garcia, and today I'll be presenting our Senior Design 1 Presentation Part 2 project, which is the low-cost buoy. We are the Team 16, and we'll be going over various topics. We're going to start off with globalization and our standard consideration. For globalization, overall, our device has a great chance of being successful on the global stage. These countries need to have quality data to make the right decision relating to the future of our ocean. Our plan has to take this product locally with FIU and then to expand it to other universities. Globalization is the future. What can globalization do? It can reach out to other countries. It can open up the market, increase funding, share information, eventually save money. And it has many benefits for the ocean. Communicating with other universities and receiving their feedback are ways to improve our low-cost buoy. Now, standard consideration. For standards consideration, for this project to be successful, it must follow a set of rules, or in this case, standards. For our buoy project, we will have standards consideration to demonstrate concepts of Wi-Fi, PV systems, and sensors. These standards are taken from an institution such as the Institute of Electrical and Electronic Engineers, hence the IEEE. For the first standard consideration, it is the IEEE 80211 from 2020. The purpose really is for Wi-Fi, speed, and frequency. It's provided for fixed, portable, and moving stations within local areas. For our second standard consideration, it's the procedure to size the PV system, to improve the performance and the cost effectiveness, and the lifetime of these systems. It's provided for solar panels and sizing standalone PV systems. For the third and final IEE, it is the 2700 from 2017. The purpose really is just to know the terminology and units and conditions and the limits of these sensors. It's provided for the sensor performance and the sensor parameters. And next, my classmate will go on to talk about the feasibility and risk analysis. Thank you.
My name is Juan Ramirez. I'll be covering the feasibility and risk analysis of our project. The feasibility analysis is where we figure out if our project is viable. We have a table here that we use to calculate the G mean and the weighted scores for each section. There's a total of 7 sections. Each section is compared to one another depending on the importance of one to the other. The scale is from 1 to 9, 1 being of equal importance, and 9 being the extremely more important than the other. The G mean is calculated by this equation, and the weighted score is just the G mean over the total. For the weighted average, which will give us the overall score of our project, we use the previously analyzed score individually of each section, and also the weighted score of the previous chart. To get the weighted score, we get the score times the weight, and we get a weighted score. Also denoted in the table as W dot score. To get the weight score average, we use the sum of the weighted scores over the sum of the weights to get a total of 4.18. The weight average is 4.18, and it is greater than 3, thus our project is viable. For the risk analysis, we have a Fishbone chart and a risk threat matrix. For the Fishbone chart, it goes in ascending order to the right, meaning the most important section that we discussed was to the rightmost topic, which is schedule. We also made a risk threat matrix, which identified the likelihood and the importance of each risk threat that we identified. It has different classes. Each class in ascending order from class 1 to class 4 of the amount of monitoring that each risk requires. For our actions to minimize risks, we made a table where we took all those risks that we identified and looked to actions that would minimize the risks of those happening. And as a team, we thought that monitoring our schedule and monitoring the cost of the project were the two most important sections to look at, since those were the most likelihood to happen and the most likely to affect the project's success.
Hi, I'm Daniel Cabrera. In this section, we're going to be talking about the plan of action and how vital it is in an engineering project, because this is where most of the organizing occurs. Key factors in accomplishing a team project goals include dividing the project into different phases and tasks. This section also mentions the statement of work, the work breakdown structure, and how they are essential in generating our Gantt and PERT charts. The work breakdown structure is a valuable tool when seeing the project as an outside source. It allows the team to visualize the project separated by phases and tasks. Our work breakdown structure shows the tasks that need to be completed in each phase to move on to the next. For example, here we have in phase 1, project research. We must complete these 4 tasks in order to move on to phase 2, hardware design. Project management is extremely important when designing a successful product. For product management, we must consider important factors such as time management, assign individual responsibilities, and performance goals. A useful tool we must consider when implementing project management is the Gantt chart. Here we have the Gantt chart. As you can see, we started our project on May 9th, and if we follow the timeline, we should be completing around December 9th, 2022. The Gantt chart is able to split the timeline in our different phases and tasks, showing the separate completion dates. In this chart, we have the ability to dedicate certain tasks to each individual, helping as a guide towards a smooth project completion, keeping each team member goal-oriented. Here we have the PERT chart. The PERT chart is a program evaluation and review technique chart. Just like the Gantt chart, it is a very useful tool when coordinating and managing a project. This chart is shown as a flow chart, which focuses more on the independent task relation instead of the time required to finish a project. The tasks can be situated either sequentially or in parallel, as you can see here. This helps design our critical path. The critical path is a stretch of activities that will take the longest to complete. Once we've identified which phases and tasks are on our critical path, we can better set the sequence of steps to follow when completing our project. In conclusion, the plan of action is an extremely important section. In this section, the team was able to manage and plan our tasks to help reach our goals in a timely manner.
Hello everyone, my name is Juan Nunez. This is Multidisciplinary Aspects. Our team is composed of 5 members from the electrical and computer department. Our team leader is Hernando Ramos. As a team leader, he's in charge of making schedules and assigning roles for our team. Regular team members include Juan Ramirez. He's our software developer. He's in charge of programming the Raspberry Pi. Daniel Cabrera, he's our circuit designer. He's responsible for supplying power to the Raspberry Pi and sensors. Johan Garcia, he's our pro designer in this team. He's in charge of making the shape of the water buoy and where do the sensors and putting the sensor where they go. And then lastly, myself as Juan Nunez, I'm going to be working as the hardware developer for this project, basically tasked with doing the pinouts for the Raspberry Pi and how they connect to the sensors, and basically how everything interacts together. Here is our education and skills and experience. Hernando Ramos, his education is in computer engineering. He has knowledge in Java, Python. He has taken a couple classes in ethical hacking. He has programmed FPGAs, Raspberry Pis, and microcontrollers. He has worked for Apple for 12 years as a technical support. Then we have Daniel Cabrera. His education is on electrical engineering. He's efficient in AutoCAD, and he has knowledge in circuit analysis. His concentrations are power and control systems. He has worked as a field supervisor at Heaven Bound. Heaven Bound is a construction company. Juan Ramirez, his education is in computer engineering. He has general knowledge in Java and Python. His concentrations are in embedded systems and software. He has a lot of experience dealing with microcontrollers and also programming them. Then we have Johan Garcia. His education is on electrical engineering. He's also efficient in AutoCAD. He knows how to solder. He knows how to do electrical analysis. His concentrations are autonomous systems and robotics. He has competed in robotics competitions before. And lastly, myself, Juan Nunez, my education is on electrical engineering. I have knowledge in programming languages like C, C++, Java, Python, math software, knowledge in MATLAB, and electrical analysis and multisim. My concentrations are in embedded systems, software, microcomputers. I have worked with Raytheon Technology as an electrical engineering intern. Here's our budget. Basically, these numbers represent hours. So we have done 65 hours for research. We have done 52 hours for hardware design, and we have done 69 hours of software design, and lastly 88 hours for testing. This is assuming $15 per hour, meaning that if we add all these numbers and then multiply times 15, we're going to get a total cost of $4,110. Thank you for watching. I'll leave you with my fellow teammate.
My name is Fernando Ramos, and I'm going to describe to you what the lower cost buoy looks as an end product and what we hope to deliver by next semester. We're going to do this by several block diagrams. Level 0 goes over base functionality. We're going to take in sunlight and readings from our sensors, and we're going to output a cellular link that will then transmit that data that we've gathered from the local body of water. Diving in deeper to level 1, we're going to look at how that sunlight is taken into a solar power system, which powers a microcomputer, which also receives the temperature, conductivity, and pH level of the water via these sensors, and outputs those out via that same cellular uplink that I mentioned of that water quality. Looking at level 2, we're going to break down the solar power system itself. It takes in sunlight to a photovoltaic module, which will then go through a charge controller to create a regulated DC power output, which will charge the lithium polymer battery. We're then going to look at the level 2 of the microcomputer itself. It's going to take in those readings and that power generated through a GPIO header, which will then connect to the main processing unit on the chip. And then we're going to connect to the wireless portion of that chip, and using an RF antenna, we're going to create a cellular uplink through which that data is going to go out. Looking at the program that's going to run the microcomputer, this flowchart here goes over how the program's going to check to see if the chip is on or logging. If it's not, we're going to go ahead and start that log, outputting every 15 minutes. Then we're going to check to see if we can establish a connection with the server. If we can, we're going to send that data out. If we can't, then we're going to go ahead and start over. At any point, if we can't connect, if we're not powered or if we're not logging, we're going to turn off that antenna to save power as much as possible. We hope to deliver by the end of next semester a list of components that we need, a schematic of the low-cost buoy itself, and a working prototype to present at next semester's presentation. So to conclude our presentation today, we went over the global impact of our low-cost buoy, both locally and internationally. We went over the different standards that we have to consider when creating this low-cost buoy. We went over the analysis of feasibility and what risks we can encounter and how to overcome those. We created a plan of action to ensure that we can get this done by next semester and have a working prototype to show. We also broke down our personnel and all of the different multidisciplinary aspects we bring to the table and all of our skill sets and how they mesh well together. We created a budget with the help of our sponsor, and we ensured that we had a design that could be created at a low cost. And then I went over and described for you what that end product is going to look like and what we hope to deliver by the end of next semester. We're really excited about this project, and we hope to bring you that prototype soon. Thank you so much.